Okay, welcome everyone. Thank you for coming. I hope you still enjoy topology. Today we will see kind of the main theorem, at least the main theorem about surfaces, my prime number decomposition, so the prime factorization that I promised last time. And this is really key, so I will stress that several times. I will also show you the proof. It's kind of nice, it's not so bad, but if you want you can ignore the proof. The main point will be the statement. Okay, so let me recall what we have seen last time. So last time I did a lot of calculations with this funny hash product. And kind of the key one at the end that I did is this one here. Torus hash projective plane is the same as Klein-Bottle hash projective plane. And we'll see that this is kind of the, so in my prime number decomposition theorem, in my prime number theorem, this will be kind of the slight annoyance. And there won't, otherwise the statement is kind of really beautiful. And that's a slight annoyance here, and you always need to be careful, and I try to stress that several times. And what really happens here is, and that's why I call this this slide, the projective planes, they dominate, right? So we kind of don't like them, they're a bit difficult, but they essentially dominate everything. So as soon as you have a projective plane, everything else looks like a projective plane. It's very weird. But if you just think of this equation here, and the k actually itself is twice the projective plane, so projective plane, hash projective plane, then you can kind of get rid of a torus by picking up more projective planes. As soon as you already have a projective plane around. So kind of projective plane, as soon as you have one of them, they just multiply like crazy, and you have like thousands of them, huh? Right? They they dominate everything. So we kind of can't ignore them. We like to want to ignore them. They're a bit difficult. They live in 4 space, kind of really strange objects. But we can't, because they eventually will dominate the whole picture. At least the whole picture for non-orientable ones. Will be more precise in a second. And the calculation was rather involved. It was not so easy. It was not super difficult either. But the projective plane is kind of a kind of weird object. It kind of takes away, it just takes everything it sees and turns it into projective planes. It's kind of a very strange behavior. It's very different from numbers. Right, so that's just what I said. So we just really have 3 copies of the projective plane as soon as you have a torus. So whenever you see a torus, let's say you have 5 tori now, and you have 1 projective plane, the projective plane will turn the 5 tori into 10 projective planes. And always multiply by 2. So it just dominates everything. Okay. And this really means, or I write it suggests, but in the end it means, as soon as you take any surface and you put in a projective plane, it's automatically non-orientable. The projective plane just destroys everything you want. It's kind of a very dominant object. And that's why it is so important. Right? One warning here. So in usual numbers, you would have something like, let me write down an equation. So here, for example, this could be 2 times A equals 2 times B, for example. Maybe I should write it the other way around. Let me try again. So A times 2 equals B times 2. And you would just say, OK, we want to find A and B. And in usual numbers, you would just say, OK, well, fine. We can just kill this one. We just divide by it, and that's good. And we know A equals B. Yeah? This calculus here, our hash product, it behaves like multiplication. But the one crucial difference is you can't do this trick. So I can't just say this one goes away and this one goes away, and T is K. It doesn't work. So you're not allowed to do that. Otherwise, you should think of hash as being a nice multiplication. So we are not allowed to do that. So let me get rid of it. Right? So in numbers, that's perfectly fine. But on hash, on surfaces, it's not. And this is exactly why this projective plane can have this funny property that it just kind of eats everything and just spits out copies of itself. And the projective plane can have this property because this calculus doesn't have this constellation type property. So in numbers, you will never see that. But the projective plane is kind of really interesting. It's kind of, this is dominating, right? It eats everything you throw at it and spits out more projective planes, essentially. Kind of a very strange object. Okay, right? Right, and we have seen that they are not the same For example, one of them is orientable, the other one is not, right? So T embeds into 3 space. It was just a swim ring. I can also draw it, but I can't draw K. So K was this guy here, where you have a regular annulus on one edge and a twist on the other edge. So you bend it to an annulus and then kind of twist it again, and you get this funny bottle type of object. Yeah. So they're not the same, so you can't cancel here. But they will turn into projective planes anyway, so this is kind of the main equation. So everything is a projective plane. As soon as you have one projective plane, everything is a projective plane. It's kind of really strange, but it's kind of also a little bit of fun. Okay, so what I'm aiming for is to just state now the main classification theorem, the prime number theorem, the prime factorization theorem, that's what I should call it. So let's just have a look at more projective planes, I guess. So what is the difference if I look at a projective plane and a torus? Okay. Okay. So there are several differences you will spot, but one of them is kind of interesting and kind of combinatorially really beautiful. So for the projective plane, let's say you start reading here. For the torus, you start reading here, and let's say we go around this direction. So we read around the polygon, then we will pick up AA here, right? For the projective plane, we pick up AA. And here we pick up something like A, B, then we walk A backwards, so let me call that A inverse. So backwards is just denoted here as inverse. And then I walk B backwards, B inverse. All right. So in particular, we see this funny pattern here that we have the symbols appearing with the same exponent for the projective plane. So they're both pointing in the same direction. But not for the torus. They're always pointing in the opposite direction. And if you think about what happens under gluing, pointing in the opposite direction is the nice gluing because they turn one around. So pointing in the opposite direction is gluing without twist, and pointing in the same direction is kind of putting in this twist like for the Möbius strip. So this should tell us something. And the easy, no, it does. So it's very easy to decide whether a polygon is orientable or not. So you only need to look for a pair of edges which points in the same direction. They could point both clockwise or counterclockwise. It doesn't make a difference. They just need to point in the same direction for paired edges. Okay? And let's just do it. So we call one of them an oriented pair, and we call the other one an unoriented pair. So this is my oriented pair. And if you think of gluing again, then this is kind of the nice gluing. So this is without twist. And this is kind of the twisty gluing. So this is glued with a strange twist. Right? So the right-hand side should be somewhat more difficult, because if you would just take it in your hand and try to bend it out of paper, it will be very difficult because you need to put in a twist. Okay, let's just call it right now oriented if they point in opposite directions, and unoriented if they point in the same direction. Again, in what direction they point doesn't matter, just opposite or same. Okay? And I call it oriented or unoriented. And note here, I said again, very easy to check on the polygon. Right? The torus, just look at it, has only oriented edges, and the projective plane has this one unoriented pair. Really easy to check. Just look for the pairs and look whether they point in the same direction or not. That's just what I said. So in somewhat, you should already believe me right now that probably the unoriented case is a bit more difficult than the oriented one, right? So we can fold them together nicely for the oriented case, and for the unoriented case we just can't. Okay. So in some sense this is kind of difficult here. So this is kind of, we don't know what to do, and we kind of like this one. Okay. So let's try the following. So whenever I have an unoriented pair, it's somewhere in my surface, in my polygon, I can just connect them like this. There's a C and a D. And what you see now is a Möbius strip, right? So this is exactly the twist. So if I just draw this one again, there's a B and a B pointing like this. And maybe I get the colors right. Here's a C and a D pointing like this, right? So that's our picture of a Möbius strip. In particular, as soon as you see an unoriented pair, the surface is not orientable, hence the name unoriented. So every unoriented pair says that there's Möbius strip somewhere in your surface, just by doing this little picture trick here. So already, okay, very good. And so this implies, I will say that later again, but I can already say it here, that checking unorientability is really simple. It's unorientable if and only if you find an unoriented pair. So just look for the paired edges and see whether they point in the same direction or not. That's a 0 or 1 question. So it's either true or false. You just need to find one pair. Because one pair, you have found one Möbius strip. Right? Okay, I hope that's reasonably clear. So this last condition we had the Euler characteristic, we had the number of boundary cycles, and we had this slightly obscure condition of being unorientable. It's actually really, the last one is actually really easy to check. You just need to look at the polygon and search for edges that point in the same direction. Very simple. It's really, really simple. And you get an answer yes or no. It's either yes or no. So projective plane, it's a yes. You can see the AA. For the torus, it's a no. Everything points in opposite directions. Okay, so that criterion is also fairly easy to check. And then we get the following main theorem, our prime number theorem. I will reformulate it a little bit as we go along. But essentially, it's already here on the next slide. Okay, let be a connected surface. Okay, well, what do you do if you don't have a connected surface? Well, you just do it component-wise. You have something here, you have something here, maybe you have something here, whatever it is, something with a hole. Well, you just do it component-wise. Okay. So the connected is just making my life easier to write it down. Okay. But anyway, here's my prime number decomposition. So then there exist those numbers, D, P, and T, disks, projective planes, and tori, so they index those numbers, such that our surface is actually just a sphere, and then hash it with, well, D disks. So put in, we have nice pictures later, so put in holes, D holes, with P projective planes, or with T tori. Right? So in our prime number decomposition, we only have 3 prime numbers, if you want, the disks, the projective planes, and the tori. Okay. And it's non-orientable if and only if P is 0. So if you don't have any projective planes around. Last time I showed you Möbius strip is also just a projective plane. So if you don't have any projective planes around. Okay. And that is all very nice. So 1, 2, 3. So 1 is really a prime number decomposition. I hope that's reasonably clear. It's just 3 prime numbers. So it uniquely determines the surface by just finding D, P, and T. It uniquely determines the numbers by just finding, let me just write it like this, 3 to the P, and let's say we only have 3 prime numbers. Yeah, I should be able to find the next one. Probably it's 5 to the T. Let's say we only have 3 prime numbers, then every number would be determined by finding the power of those prime numbers, right? And that's exactly what this statement says. It's just for disks, projective planes, and tori. Fantastic. And then this is a funny extra condition. So we can always assume that P times T is 0. So why can we always assume that P times T is 0? This is just saying one of them is 0. Either P is 0 or T is 0. Okay, if P is 0, yeah, well, then P is 0. Fine. But if T is, so if both are positive, let's say both are positive, so P is something and T is something. I will do that in the formal proof in a second. But then you have this equation from before, then the projective plane hits a torus, and whenever you can do that, you can replace the torus by more projective planes, because the projective plane is dominant. So as soon as one of them is positive, you can just replace it, and you get more projective planes. So you can always assume that P or T is 0, and it's unorientable if and only if P is 0. And this is a pretty cool theorem. It just determines completely the surfaces. So all surfaces of this form, and that's it. Which is kind of a really amazing type of statement. Right? It's not that difficult. So it remains kind of to find those numbers D, P, and T. Okay, I leave it up for a second. we will see some reformulations later on. Okay. The funny sphere, you might wonder, why do I keep the sphere around? Wasn't the sphere the identity? Yeah, well, the equation doesn't really make sense if all of them are 0. But otherwise, you can just think the sphere is just this funny thing that there's one number that is annoying to write down in prime number decomposition. That's the number 1. So it needs some special treatment. The sphere is a little bit annoying to write down, so it needs a special treatment. And that's why I put the sphere in front. But really, your focus should be on this part of the game. So I just have the sphere for exactly the same reason that for numbers, you need to say, OK, 1 is a bit special, fine, and all other numbers are good. And here, the sphere is a bit special, OK, but all other surfaces are good. And that's why I have this sphere around, just a remark. OK, and I will show you the proof. The proof is not so difficult, actually. And then we kind of see that this theorem is already pretty good. I think it's really good. It's a prime number decomposition. And just think back where we started with surfaces. It looked kind of really wild, and what could be the classification of surfaces, and you can actually get a nice answer. But I can make it even more explicit. I can tell you exactly how to get those numbers d, p, and t. But before that, let me show you the proof. It's not that bad, so let's just do it. It's an argument by induction on the number of edges in the polygon decomposition. Okay. So let's try. And as soon as you have 1, 2, and 3 are not so difficult anymore. So let's try it. But I hope the theorem is really, really important. So try to remember this analogy with prime number decomposition. OK, we want to do induction on the number of edges, so we should start with some easy case where there's just one edge. OK, so we can easily draw all polygons with one edge. Well, since there's one edge, it's this one here, or this one here. Right? So AA in the opposite direction, in the same direction, or I call it BB in the same direction. And we already know what these guys are. So the first one should remind you of a sphere. And the second one is a projective plane. And yeah, sure, they fit into this pattern. The sphere is just dp, I can write it down. The sphere is just, let me write it down like this, 0, 0, 0. Right? So this case here, where I refer to this tuple, so d is 0, p is 0, t is 0. And the projective plane, maybe I give it a different color, is just z, 1 and 0. Very good. Right. So we are good to go. Good start for one edge. It actually works. Right? We only have two surfaces. And in this picture, they're the kind of the easiest ones you can write down, right? Because they only need one edge. And again, the projective plane shows up. So this guy, we really can't get rid of it. It just sticks around. It's just one of those facts in life that you want to get rid of, but it will not go away. It's just there. So there you go. It comes again in here. Right. I hope that's reasonably clear. So for one edge, we are good. And now we can assume we have more edges, right? So two or more. And essentially, we want to take out one edge and then argue by induction. OK, fine. So let's try that. OK, let's say it has only 3 edges. OK, so nothing paired. So here at A, a B, a C, a D, an E, whatever, something like this. Nothing is paired. So you take the piece of paper in your hand and you do nothing to it, so you found a disk. So if nothing is paired, as everything is free, we have a disk, which is exactly the case. Let me just write it down. 1, 0, 0, right? So here in this notation again. So if I'm writing tuples, I'm always in this notation. So D is 1, P is 0, and T is 0. All right. So we can assume, OK, fine, we're done. Good. So we can assume that we have some paired edge. Right? So we have at least one of them. So let's do. So let's say there can be only 2 cases. Right? It's unoriented or it's oriented. Turns out that the unoriented case is a bit easier. So let's do that one first. hope that's clear, right? We're done with the free edges, so there must be one paired edge, and it's either pointing in the same direction or it's pointing in opposite directions. There's no other way that it could be, so we are now the case is to check whether this edge is unoriented or oriented. So let's do that. Okay, let's do this case first. Turns out it's a bit easier. So AA, it appears somewhere in my surface. So what can we do? Well, so let's cut the surface like this, so along the top of the edge A. So the point is the same. Let me just mark that. So this point X here appears at the bottom of A, so it appears at the top of A. So really cutting the surface through the point X. And now we have two pieces. Yeah, we can rearrange that, just pulling it around. And it looks, it's not a really, well, let me draw it a bit bigger. It now looks like this. There is the outside of the surface. And we turn it around, put it together again along A. So to take it apart and put it together along A, the surgery operations. And now the edge A is a cut we have in here, and the B is moved to the outside. So if you do that, you will see that this is right. And note that we have the pattern BB. I hope you remember now what BB is. BB is a projective plane. So somewhere in my surface, like here, there sits a projective plane, actually. Well, this is a bad color. Maybe this one is good. So here, there sits actually a projective plane in my little surface. So if you remove that one, you have something remaining, and you just, that's essentially your induction. Right? So it's a projective plane that just sits on the side, so we can just remove it along A with the cost of a hash product. So it's P hash, a smaller one. Right? So this is the surface S, and now we have an S prime surface here. Maybe this guy is S. Now we have a smaller one with fewer edges, so we can apply induction, and what you can see is it now works. It just increases P by 1. Right? So this one has something, whatever, D, P, and T by induction, whatever it is, then it follows that this one here has the same D, a P plus 1, right? We just cut off a projective plane, and a T. Hope that makes sense. I just found a projective plane, I take it away, and I get my new decomposition kind of inductively from the old one. Hope that makes some sense. Right? So, I call it T. Okay, this is S, this is T. Fine. So the surface S is projective plane hash. An older surface, and I already told you what we want to do with the older surface. So we know inductively what the older surface is. Some D, P, and T. Right? Since T has fewer edges, I just took out 2. So we get the plus 1 here. So note this plus 1 here compared to here as required. Right? So it's actually not so bad. So what we did is the following. We took a big surface, we found a projective plane, we took it out, and then inductively argued that we know everything what's going on for the smaller surface, and pieced it together into the main statement. Okay, and the case of an oriented edge works in the same way. So let's do it. It's just a bit more difficult because there are subcases. So let me just go through it fairly quickly, and you can have a look at the slides. So this is now a subcase. So whether it looks like this or there's another subcase, whatever. It's essentially the same argument. So let's do one of them. So let's say your oriented pair looks like this. Then you can cut it in, and you get so you just push it in, and you just get a new surface which is smaller. So here's my T again. So your S and T. So you get the same type of formula. And really, in this case, S is just T. So your polygon decomposition of S wasn't really efficient. There was a silly pair of edges that you can ignore, which is kind of nice. So whenever you see a large polygon decomposition, look out for those guys, because you can always just push them in, and your polygon decomposition gets smaller, which makes your life much easier. Anyway, so this is what happens, and yeah, now we know everything for T already, so we are done. Yeah, so S is T in this case, so the numbers stay exactly the same. Fine. All right, and then the case 2a is, well, you don't have such a pair, but now something is in between. Okay. And what happens in this case, let's see. So you can now pull out a disk. So this is a disk sitting in here. So you pull out a disk and apply induction again. It's the same argument. So here's T. Now it's a disk. Now this is D, P, and T. So this will be D plus 1, P, and T. Right? So you just removed one disk. So in the unoriented case, it's a bit easier. You just remove a projective plane. And in this case, we just have a few more cases. But it's essentially the same idea. You find the smaller piece, you remove it from the decomposition, and you argue inductively. Okay, so that's what I just said. So and then again, we get the same type of statement. So we just have the increase here of d by 1 because we took out a disk. Okay, fine. And you might guess now there might be a third case, if I already call this case 2a. So we have a disk, I pulled out a disk, I pulled out a projective plane, which one is missing? So we should be able to pull out a torus as well. Let me just show you the remaining case. So here we go, and you can already see what the torus is if you just read off the word. So whenever you see this pattern, you have a torus. So let's read along here. So there will be an A, then whatever we don't know. There will be a B, then whatever we don't know. Then there will be an A inverse, whatever we don't know, and a B inverse. And whenever you see that pattern, you can pull out a torus in your decomposition. And that's exactly what I will do now. I will pull out a torus, cut it appropriately. It's a bit difficult, but you just arrange it such that the torus sits here. And now you have our little torus, and you just pull it out of the picture. Right? I just rearranged the picture to get the edges together, and I have my little torus. And I pull it out, and now I decided to call the remaining surface U. I have no idea why, so let's call it U. S and U. U is again smaller, so we can do the same. Now the equation is d p t goes to d p t plus 1. Right? So we found one torus. And this is already the last step. I just wrap it up what we have seen. So this kind of explains why we have D, P, and T. Because if you just go through all the cases, you either can cut off a projective plane, which increases P, you can cut off a disk, which increases D, or you can cut off a torus, which increases T. And there are no other cases, so these should be your 3 prime numbers, your 3 determining prime numbers. Right? So essentially what we have done is we take a large number and pulled out 1 prime and then argued by induction that the smaller number still has a prime number decomposition. We just did it on the polygons. And now I will wrap it up here, and again note, I hope, the increase of T. So all of these show up. So we need all of them. But turns out that these are, if you go through it and just write down what possible cases appear, these are all possible cases. So this is exactly the classification we want, because we can always pull out one of them. And then kind of inductively, we know that this is the correct decomposition to expect. Okay, let me repeat what we have seen. Essentially, I took a surface, or a number, whatever you want. I pulled out one of our basic surfaces, one of our prime surfaces, or a prime number, and argued by induction that the smaller one already has a prime number decomposition, so my bigger one already has a prime number decomposition. And when you compare this to prime numbers, you will see that for prime numbers you can pull out arbitrary prime numbers, so that's why you get arbitrary complicated expression in prime numbers. But if you follow this proof and just write down the cases, you will realize it's kind of fun that you never need anything more than a disk, a projective plane, or a torus. So these are exactly our 3 prime numbers. They stick in every surface, and you can always pull them out. I should say they stick in every surface except the sphere, because that's like the unit. It's like the 1. The 1 doesn't have a prime number decomposition. That's special. But in any other surface, you will find one of those. Right? So it's kind of interesting, kind of a nice result. Right? And if you just think about what I just said, in any surface you will find one of these three guys. Right? So then you should just be able to stick every surface together from those three ones. And that's exactly the content of the theorem. I hope that kind of makes sense, why the theorem should be true. So you will always find one of those three, so they should appear in our prime number decomposition. Yeah, awesome. So there are no other cases, so that's what it is, which is an absolutely fabulous formula. So I have it like 500 slides because it's so fantastic. For some numbers d, p, and t, number of disks, number of projective planes, and number of tori that we can find in our surface. Really, really nice, beautiful. Okay. Well, d is the number of boundary cycles. Why? Because d was the number of disks we pulled out. Okay, fine. And let's say if p is greater than 0, so this proves 1. Well, let me just wrap it up. This proves 1, this proves 2, and we'll have the statements in a second again. So let's just go back. Why not? Let's just go back. Very cost efficient to go back too many slides. Yeah. Ah, yeah, there you go. So 1 is our decomposition, 2 is the statement, and the boundary are the circles, so just the disks, and the disks you put into the surface. And the last statement is the statement with p equals 0. It's non-orientable if p equals 0, so let's have a look at the last statement. Too many slides. So where are we? We did this one. Yeah, here we go. Okay, so if p is bigger than 0, then there's a projective plane in my surface. So that's a Möbius strip in my surface. That's essentially what you did, right? So it's orientable, and it's non-orientable if p is not equal to 0. Okay, and actually, if p is 0, then you just have a torus with, I can draw that picture now for you, because this one actually is drawable. Okay, so let me draw it for you. In this case, I just have a torus, so p is 0, where I have t of those guys. These are handles, very ugly handles, but anyway. I will have a nicer picture for you in a second. And these are d of those guys. So I can stick it in R3. I just draw a picture for you. So it's actually orientable if p is 0. So it's orientable if and only if p is 0. Right? So if p is bigger than 0, there's a projective plane. So we find a Möbius strip. If it's exactly 0, I can just draw the picture, and there you go. It's clearly lives in R3, so it's an orientable surface. Okay, that's it. It's not so bad, actually. Mind how kind of fantastic and strong this statement is. We have now classified all possible surfaces. Remember, like 2 weeks ago, that seemed like completely impossible, but it's not so difficult. And the whole trick is to use this funny hash to pull out the basic prime pieces of the theorem. Fine. Okay. And I want to make it a bit nicer. Remember that we had this funny fact. Yeah. So whenever you have a projective plane and a torus, so both of them are non-zero, then you can always replace the tori by more projective planes, because the projective plane is really, you throw something at the projective plane and it just spits out more copies of itself. It's just a really strange object. But anyway, so you can get rid of all tori in this case. So you can always assume, so if you have t copies of a tori and one projective plane, you can just pull in more projective planes and just get rid of all tori until you just have zillions of projective planes. Just do it. Get rid of all tori. So we can always assume that t is 0 if p is not 0. Right? We can always just pull out more projective planes instead of tori. So that's the same as just writing this condition, because this condition really just says that, right? So one of them is 0. Right? So if p is 0, we are in this case. So this is p is 0. And if P is not 0, use this funny thing here to just make everything into a projective plane. So tori actually vanish. That's interesting. Okay. So the reformulation of the theorem, let me just skip the remaining parts and let's go to the corollaries. So there's one more slide where the theorem continues. Let me just skip it for now. So a surface is non-orientable if and only if its polygon decomposition contains an unoriented edge. So you just need to find one of them. Why? Because that's a projective plane that we just cut out, right? Remember the first part of the argument, there was an unoriented edge. We pulled it to the side, and it looked like this. There was a B, and a B, and a rearranged A. I forgot the color that I used for A. Something like this, which is really just a projective plane in your surface. So as soon as you have one unoriented edge, doesn't matter, one of those, doesn't matter where they appear, they could appear very far apart or whatever. As soon as you have one of them as a projective plane in your surface, and it's non-orientable. It's really easy to check. It's an if and only if, so it's really, really easy to check. So this funny last condition of being orientable or not is actually really easy to check. Just look at the edges, and that's essentially what you need to do. Okay, and the proof was exactly this. You cut out the Möbius strip, or if you like the other one more, you rearrange it, and you cut out the projective plane. Okay, and this is kind of the form of the theorem that I like the most. It's stated slightly differently. So first stays the same, second stays the same, but I kind of exchange the last condition for the one that looks a little bit nicer. It's orientable if and only if P is 0. Okay. But otherwise, it's just the same thing again, just rearranged a bit. And now comes something important. Now we want, if you have a number, whatever, 10, then you want to write it as 2 times 5. Okay, fine. And we want to do the same. But we have one ambiguity, which is exactly this funny, the projective plane needs everything. So projective plane and torus is 3 copies of the projective plane. So 3 copies of it. Okay, so that's kind of an ambiguity because both of them are prime numbers. The way to get rid of it is the following. And we call that the standard form. And I'll show you pictures for the standard form in a second. The standard form is a DPT composition where either P or T is 0. So you never have the mixed cases. So either P or T is 0. Whenever you have a torus, you don't have a projective plane. And whenever you have a projective plane, you don't have a torus. And that's the prime number decomposition we want. Right? So we have this funny ambiguity, and we get rid of it by just saying, okay, if we have a projective plane, everything is a projective plane. And we call this the standard form. And this is kind of really important because this is kind of the outcome of the whole classification. We can now check whether 2 surfaces are the same by writing down the standard form. If they have the standard form, they are the same. This is an if and only if. They are the same if and only if they have the same standard form. Okay. Standard form is really my favorite equation here, and only where either T or P is 0. And the last point tells you exactly when P is 0, namely if and only if it's orientable. Okay. This is the whole outcome of our discussion up to this point. We have a prime number decomposition, which we call a standard form. And from that form, you can read off everything you want from your surface, or about your surface. I hope that's reasonably clear. So we really want to know that standard form, right? That's kind of the whole point of this classification. It's not bad. It's actually pretty nice, but we really want to know it. The standard form uniquely identifies our surface. So definitely want that. And we can read off orientability and whatever just from the standard form, right? We can read off the number of boundary cycles from the standard form. We can read off the Euler characteristic from the standard form using that formula, which I postponed to the tutorials. So it's really easy. So you can read off the Euler characteristic if you know d, p, and t. Just formula, 2 minus d minus p minus 2t. Nothing fancy, just a really simple formula. So we know everything about our surface as soon as we know the standard form, like everything. Right. And for a not connected one, we would want to put everything in standard form, right? So if you have here a surface, and here's one, and here's one, whatever, you just want to put all of them in standard form. So this should be in standard form, this should be in standard form, and this should be in standard form. Fine. And this uniquely identifies our surface, and we can read off everything we ever need from that decomposition. So your first question always should be, what if I have a surface and you don't know what it is, can I actually find those numbers d, p, and t in standard, so that my surface is in standard form? Because then you're done. You can identify the surface explicitly. That's a wonderful, absolutely wonderful theorem. So let me mark the formula again. It's just very important. Okay. Okay. And it's kind of the same as writing it like this. That's the statement I promised from before. Okay. So if we have any of them, if we have all of them, then we have found our surface. Let me skip the proof, and let me just show you how the pictures look like. What are the standard forms? We already know how they look like. It's kind of interesting. So the cycle closes, right? So we started with some easy pictures, and it turns out that there's nothing more, but you need to work a bit actually to see that. Okay, so what is, let's say d is something, and p and t are 0, then this guy is a sphere with d punctures, and here are my pictures. Okay. So the sphere is one hole. I have some other picture in a second. So you have one sphere, and you puncture in once with your finger. Or you can do that twice, or 3 times, or 4 times, or 5 times, or 6 times, or 7 times, 8 times, 9 times. Well, we know that surface already. It's just take a soccer ball and puncture it. There you go. So these ones are pretty easy. And yeah, they show up in real life. Yeah? So this is just the one with d punctures. The soccer ball itself is the one with 0 punctures. And they show up in real life. So this is a soccer ball. And if you put in one puncture, you get the other picture. And you have punctured, and the air no longer comes out. And this is the one with 1 puncture. So this is S2 hash D1, D2. This guy here, and this is just S2 itself. I think of this point as just being closed. It's just a soccer ball, like filled with air. And you put in 1 puncture, and that's exactly what happens. So we know already those guys. And now we identified them in a more mathematical way. Very good. So we already know those guys. So what are these? Let's say t is the only interesting number. We already have seen those before as well. So this is the first one. Well, let me draw it like this. I just put in a little handle on a sphere. Okay. This is the second one. Let me draw it like this. I just put in 2 of them on the sphere. So I hashed t twice to the sphere, and this is how it looks like. 3 of them, I just put 3 of them to the sphere. 4 of them, I just put 4 of them to the sphere. And so on. And so on. And just do it again. And we already know those guys. We've all seen them already, right? This guy. So here's another picture of it. It's like type of whatever. In the case where it's just there's air inside. So in the case when there's just one handle, this was the swim ring, right? And you can just draw them. And that's the standard, one of the standard form guys. Not so difficult. It's not so difficult. Let me do it again. So here you just, this one is a picture. I just put it on the sphere. Or, too many pictures. Put this one on the sphere, right? So it depends what I want to do. So I need one more picture because I have 3 prime numbers. And the last one is not really nice to draw. So I just draw it as follows. So it's really difficult to imagine. So this is a picture of the projective plane in 3 space. It's really a difficult object. So I'm not quite sure how to draw that. And instead of trying anything, I just put in a little warning thingy, a little colorful hat as a sign that there's a projective plane. And it's really difficult to draw. I need 4 dimensions to do it. I only have a 2-dimensional slide, so I don't know what to do. I just put in a little warning thingy. So projective planes are always a little bit complicated, and I put in more and more and more, right? 6 of them. Kind of the same idea. You just decorate the S2 with some little picture. I can't draw it, so I just put in a little thing that reminds you that this is a little bit dangerous if you want. Okay, so here, there's another example. We can now do it, 8 and 7. If I haven't miscalculated, there should be 8 punctures and 7 handles. This is how those guys look like. 6 and 9. I draw 9 of the funny ones and 6 of the punctures. You never have those guys in standard form because I can always replace a torus by a projective plane. So this is not in standard form, so not in standard form. Yeah, what we rather would draw is this guy here because you can always replace those ones by projective planes as soon as you already have one of them. So this is good, this is standard form, this is standard form, and this is everything that appears. So this is a complete list of surfaces. So it's either of the first type, it's of the second type, or it's of the third type, with arbitrary number of decorations. Right? And that's a really cute classification, actually, right? The first ones are like the things we already know, like swim rings with holes. Well, not really good for swim rings anymore, but something like that. The second one, yeah, okay, projective plane is a bit crazy. Yeah, so that's what it is. So you only have those 2 guys. So this one here is, of course, these are, of course, the same. So you only ever have those 2, which are our standard forms. It's really simple. It's not so difficult, right? And if we can even draw them, if you allow me to call this one a drawing of a projective plane. Yeah, so this is really beautiful. And I just write down an algorithm what you can do. So and we'll do that kind of very important calculation you do. Whenever you see a polygon decomposition, you can put it in standard form following this algorithm. Find the vertices, count the number of boundary cycles, that gives you D. Look for non-orientable edges, that gives you P. And compute this guy, that gives you T. Okay, and well, this is essentially where my story ends today. This is something we will just kind of do, one needs to do in practice several times. It's very easy in some sense, but of course if you do it for the first time, like everything you do for the first time is difficult. But it is an algorithm that determines for you the standard form, and the standard form is all we ever needed to know, right? So if you do this, I just did it here. Okay, so let's say you have given a polygon decomposition. I just marked the edges or the vertices already. So let's count. I have an X, I have a Y, I have a Z, I have a V. So I have 4 vertices. Number of vertices is 4. Number of edges goes up to H. So number of edges is 8. So the Euler characteristic is 4 minus 8 plus 1. So minus 3, if I'm not miscalculating right now. Okay, so we know Euler characteristic already. Do you see an unoriented pair? I see an unoriented pair, F and F. Right, so F and F. Fine, so P is not 0, T is 0. Okay, so you see it already here. T is 0, P is 0. If you do the calculation, you will figure out that D is 1, and then you can just solve using this formula. So if D is 1, this one is 0, and this one is minus 3, we just have minus 3 equals 2 minus 1 minus P, so we can just solve for P, and we'll find the standard form is given by 1, 0, 4. It was obviously a bit quick, but essentially what I'm trying to say is there's an algorithm. You can just do it on the polygon, and you will get the numbers, which solves our main problem. So yeah, this is all I wanted to say today. Our main problem is solved. We have an algorithm to decide whether the class of a surface. So enjoy your weekend, and I hope to see you next week. Thank you so much.